Alright, let's look at 10.5 case number 3, where the denominator has a non-repeated irreducible quadratic factor. So an irreducible quadratic factor means that the solution to the quadratic equation is those of complex solutions, and it's non-repeated, meaning that you have just distinct quadratic irreducible factors. And so when that's the case, the partial fraction decomposition is going to be of the form ax plus b divided by ax squared plus bx plus c. And one thing to note from this form is that when we're seeing that the denominator is quadratic, the numerator is written as a linear factor. And when we saw in case 1 and 2, when the denominator was linear, the numerator was a constant. So you had a degree 0 on top and a degree 1 on the bottom. In cases 3 and 4, you're seeing that there's a degree 1 in the numerator and a degree 2 in the denominator. So hopefully that becomes a helpful way to keep track of how to set these up. And so in this case, we have one distinct linear factor and then one quadratic irreducible factor. And we're going to set up our partial fraction decomposition as a over x plus 1 plus bx plus c over x squared plus 4. So we can have different types of factors in the denominator. It's just a matter of recognizing those ones and applying it correctly. And the way that we're going to solve for a, b, and c is to clear the denominators by multiplying what each other is missing, and then solve for the a, b, and c. So I can multiply this by x squared plus 4 on both sides, or on top and bottom. And I can multiply this other term by x plus 1 on the top and bottom. And now that all of the denominators are the same, we can go ahead and just leave the numerators on top and distribute. So I am going to write this left side as, I'll write it as 0x squared plus 0x plus 1. And you'll see why in a moment. So I'm going to distribute the a. I'll have ax squared plus 4a plus, and then multiply it here. I'm going to be left with bx squared plus bx plus cx plus c. And now I want to group my x squareds, my x's, and then my constants. And this is why we're seeing I wrote 0x squared plus 0x plus 1. So when we group the x squareds, we'll have a plus b times an x squared, and then the sum of b and c times x plus 4a plus c. And both of these sides are the same, and the only way that we can find the a, b's, and c is to equate the coefficients. So you have your x squared terms, which leads to 0 equaling a plus b. And you also have 0x has to equal b plus cx, so this leads to 0 equaling b plus c, and then 1 has to equal the constant, the 4a plus c. And so from here, you want to just pick a way to solve this system of equations, and the way I do it may be different than the way that you do it, but right now I'm seeing that I can multiply this maybe second equation by a -1, and so I can cancel the b's, get an equation of in terms of a and c, and then solve that system. So I'm going to have 0 equals a plus b, and then I'm going to rewrite this as -c minus b, because I distributed a negative there. When I add these up, I'll get a plus c. The b's cancel, so then this means a equals -c. And so if a is -c, oops, sorry, hold on. It's not a plus c, it's a minus c is equaling to 0. So then this means a equals c. So now I can plug in a for c, and I'll have 1 equals 4c plus c, giving me 1 equals 5c, which leads to c equals 1/5. This implies a equals 1/5, and so we need to solve for b, and I'm just going to pick maybe this first equation. So if a plus b is 0, then a equals -b, so then b is -1/5. This means that now I have my a, b, and c, I can plug them in here, and I can rewrite this expression. So let me erase, and I can now say that this is equal to 1/5 times x plus 1, because my a was 1/5. My b and c, my b is -1/5, my c is 1/5, so I might as well just take out that 1/5 and write this as -x plus 1/5 times the x squared plus 4. And so this is my answer. And again, if you were to go ahead and add this up, you will get this back, so that's a great way you can check your answer. Alright, I'll see you in the next video.